Water is the only resource on Earth that we can't create more of. We can only clean what exists. It gets dirty, we use it, we pollute it, and manure contaminates it, but we need clean water. Every day, we consume hundreds of gallons of water, used for showers, dishes, and toilets. But where does all of it go? Before that water can safely return to rivers and lakes, it must go through a detailed cleaning process. Journey begins at the treatment plant. The first step is called screening. The wastewater passes through bar screens. These are massive metal gates with roughly an inch-wide gap. They catch large objects like plastics and other debris that could damage downstream equipment. These collected materials are washed, compacted, and sent to a landfill. Next is the grit chamber, where substances like sand, gravel, and other heavy particles settle. The settling velocity exceeds the flow rate of water, allowing these particles to sink to the bottom, while organic matter remains suspended. At this stage, the water is cleaner but still appears and smells unpleasant. Primary treatment. Now we've got to the primary treatment. This part is all about sedimentation. The water flows into massive circular tanks known as primary clarifiers, often ranging from 50 to 100 feet across, and about 10 to 15 feet deep. Inside, the flow calms down, and the water spends around 2 to 3 hours, enough time for particles to settle under gravity. Heavy particles sink to form primary sludge, which is roughly half of the solid waste present. Lighter substances like fats, oils, and grease rise to the surface and are skimmed off. Slow-moving mechanical arms sweep along the tank bottom, guiding the settled sludge into a central pit where it is collected and pumped away for further treatment. The clearer water above flows over the outer edge of the tank, continuing to the next stage. At this point, approximately 50 to 70% of suspended solids and 25 to 40% of organic load, measured as biochemical oxygen demand, have been removed. Biochemical oxygen demand, BOD, indicates the amount of oxygen bacteria require to decompose the organic materials present. When the biochemical oxygen demand in water bodies is high, bacteria consume most of the oxygen, suffocating aquatic life. Secondary treatment. This is where bacteria do the heavy lifting, breaking down the pollution remaining in the water. The most common method is the activated sludge process, developed more than a century ago and still widely used today. In this stage, water leaving primary treatment is directed into aeration tanks, large basins that are continuously supplied with air. Inside the tanks, billions of microbes reside. These microbes consume the organic waste in the water. The wastewater stays in these aeration basins for about 6 to 8 hours. During this time, the microorganisms multiply rapidly and begin forming visible clusters called floc. The water often appears brown and slightly foamy due to this activity. After aeration, the water flows into secondary clarifiers. These look similar to primary clarifiers but serve a different purpose. Here, the microbial floc settles at the bottom, leaving clear treated water at the surface. This clarified water, containing about 85 to 95% purifications, flow over the edge. Most of the settled microbial sludge is pumped back to the aeration tanks. This maintains an active population of microorganisms ready to treat incoming wastewater. That's why it's called activated sludge. Any excess sludge is removed for processing to prevent an overgrowth of microbes. At this point, the water may appear clean but could still contain harmful pathogens. Tertiary treatment. Tertiary treatment offers an additional level of refinement, employing several advanced methods depending on the remaining contaminants and the intended use of the water. Some plants run the water through sand beds or specialized membranes to trap remaining fine particles. Others add chemicals that bind to nutrients like nitrogen and phosphorus, removing them before they cause harmful algae blooms in natural waterways. In more advanced systems, activated carbon is used to capture tiny contaminants such as pharmaceutical residues or other dissolved pollutants. The final critical step is disinfection. Even clear water can carry disease-causing organisms. Most facilities use chlorine, dosing the water with chlorine-based compounds to neutralize harmful bacteria and viruses. Another approach is ultraviolet disinfection. By exposing the water to UV light, treatment plants damage the microorganism's genetic material, preventing reproduction. This method has gained popularity as it avoids leaving chemical traces. After disinfection, the water undergoes testing to ensure it meets all regulatory standards. Only when it passes the test can it be released back into the environment. This completes the journey from your home to the natural world with safe, clean water. The entire process operates quietly every day, handling billions of gallons. It demonstrates that although we cannot create new water, we can recover and restore the supply we use. If you found this information helpful, please like this video, share it with your friends, and subscribe and turn on the notification bell for more engineering and metallurgical content. Thank you for watching, and see you in the next video.